on Thursday, we started setting up Lagrange multipliers, which told us optimal points when we had some sort of constraint. So the problem that we've been working on, we had x to the 2/3, y to the 1/3, but we had a budgetary constraint where it was $100 for each of the materials that we were going to use. So we had this constraint 100x plus 100y minus $378,000 because the $378,000 was our budgetary constraint. So to set up the Lagrange equation, remember we did our function minus lambda times the constraint. So once we had our Lagrange equation set up, we were able to take the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to lambda, as you can see. From there, we took our partials with respect to x and y, and we solved both of them by putting lambda on the other side. When we put lambda on the other side, remember what happened was both the functions ended up equaling lambda times 100. So if they equaled lambda times 100, then they would equal each other. So we set them equal to each other and we began our algebra to solve. We divided both sides by the x to the negative 1/3 term and both sides by the y to the negative 2/3 term. We did some simplifying algebra and ultimately we ended up with 2y equals x. Okay? So once we had that, once we had a relationship between x and y, we went to our partial derivative with respect to lambda, the constraint, and we plugged in 2y for x. So now we had a function all in terms of y, which allowed us to solve for y. And ultimately we found that y equals 1,260. Since x equals 2y, x was 2,520. So we found our optimal point, but we still had a little more work to do. To get the actual optimal value, we need to take that point and plug it back into the original function. So for x, we're going to be plugging in 2,520, and for y, 1,260. Our original function, remember, was x to the 2/3, y to the 1/3. So for x, we have 2,520 to the 2/3 times 1,260 to the 1/3. You can carefully plug that into your calculator, and we're going to get 2,000.13 as our optimal functional value. So there's one more piece of information that we should consider here, and that's lambda. Right? So we used lambda when we were solving, but we never actually figured out what lambda was or what it does or what it means. So if we go back to either one of our equations, we can solve for lambda. Okay? So let's go up for a second. If we take our L sub y, we have 1/3. Now our x is 2,520, the 2/3. Y to the, we'll tell them what y is. 1,260 to the negative 2/3 minus lambda times 100 equals 0, right? From there, we end up with 0.529 equals 100 lambda. Okay, so when you crunch all those numbers carefully in your calculator, we get 0.529 minus lambda times 100 equals 0, or 0.529 equals lambda times 100, or ultimately, we divide both sides by 100, we're going to get lambda approximately 0.0053. Okay, so what does lambda tell us? Right, so lambda tells us how much our functional value, okay, is going to change for every unit that we change our constraint, right? So if we wanted to try to figure out something like what happens if our budget gets increased to $379,000, right? So $378,000. Well, we would take the amount we're changing, the 1,000 in our constraint, and multiply by lambda, okay? And that's going to tell us how much we need to change our functional value, right? So if you multiply these together, you're going to get 5.3, right? So if we were to change our constraint by $1,000, right? If we were to increase the constraint by $1,000, it would increase our functional value by 5.3 units. So it would be 2,005.43. So that's what lambda tells us. Okay, lambda is going to tell us the derivative, right? The functional change based on your constraint. So for most of these problems, we're just going to be looking at solving for the optimal point and finding the functional value. But it's important to keep in mind what lambda is telling us. So let's look at some examples. Okay, so for number 1, if you want to try it on your own, you can hit pause now, try it, and then come back and see how we solved it. So the first thing we're going to do is set up our Lagrange equation. So remember, the Lagrange equation is our function x squared plus 4xy minus lambda times the constraint, where the constraint brings over the constant to the left-hand side. So that's what our Lagrange equation looks like. Okay. So here we want to take the partial derivatives with respect to each of our variables. So the partial derivative with respect to x will be 2x from the first term plus 4y from the second term minus lambda times, now the derivative of x is just 1, so lambda times 1, and everything else was a 0. Our partial derivative with respect to y, first term has no y's, so the derivative will just be 0. The second term, we're going to get 4x, and then again minus lambda times, now if you go to the inside, the derivative of y is just 1. And then finally, the partial derivative with respect to lambda is the negative from in front of the lambda times the constant, which is the entire parenthesis that multiplies lambda. So all of these, right, have to equal 0. So for our first term, if we solve by bringing lambda over, we get 2x plus 4y equals lambda. From our second, we get 4x equals lambda, right? So we take that, and since both of those equal lambda, they now have to equal each other. So we get 2x plus 4y equals 4x. So that tells me 4y equals 2x. If I subtract the 2x from the left over to the right. So again, I want to get one variable in terms of another. So if I divide both sides by 2, I get 2y equals x. Okay, so now I have a relationship between x and y where I've solved for one of the variables. So again, now that I have that, I can go over to my partial derivative with respect to lambda and substitute in. So now I have negative. Instead of x, I'm going to put 2y plus y minus 100 equals 0. So that's minus 3y minus 100 equals 0. If 3y minus 100 equals 0, then we know that 3y equals 100, or y equals 100 over 3. That's our y value. Remember that x equals 2y, so twice y, so x will equal 200 over 3. So that's our optimal point here. If we wanted to find the other information, we could do things like plug x and y into the function, right, our f of x. And if we were to do that, we'd have f of 200 over 3, 100 over 3. We'll plug in an x wherever we see an x, so the x squared and the 4x. And the y will get plugged in for the 4xy. If you plug that in, you're going to get 1,333.33 is your functional value. And if you wanted to solve for lambda, it looks like this will be the easiest equation to work with here. So lambda is 4 times x. So that means that lambda will be 800 over 3. So for every unit we change in the constraint, we're going to add 800 over 3 to our functional value. Okay? So if you want to try number 2, go ahead and try it. You can hit pause, try it out on your own, and then come back and see if you get the right answer here. Okay. So again, first thing we're going to do, set up a Lagrange equation. Lagrange equation is your function minus lambda times your constraint, where your constraint brings the constant over. Then we need to find our partial derivatives. Okay, the partial with respect to x. So here, the first term, we're going to get a y minus lambda times. If you go inside, we have a 5x. The derivative of 5x is 5. The partial with respect to y, the first term, you're going to get an x minus lambda times. Now you go inside, the derivative with respect to y is 2. And the negative, or the partial with respect to lambda, is negative times the constant that multiplies lambda, which is your entire parenthesis. Okay, so again, we start with our relationships with our x and y here. So we have y minus lambda times 5 equals 0, x minus lambda times 2 equals 0, right? Oops. So we solve these, so y equals lambda times 5 and x equals lambda times 2. So these are different, right? Before we always had it equaling the same thing, so we were able to set them equal to each other, but these equal different things. So in order to rectify that, we want to divide the first by 5, right? The first function here, equality, and the second one by 2. So now we have 1/5 y equals lambda, and 1/2 x equals lambda. So now they equal the same thing, and so now they'll equal each other. So 1/5 y equals 1/2 x, right? So again, you can solve for either one, whichever you prefer. So I'm going to multiply both sides by 2, right? So I get 2/5 y equals x. Okay, so now I have x by itself. So I come back to my constraint, and instead of x, I have 2/5 y. So 5 times 2/5 y plus 2y minus 100. We know that that has to equal 0. 5 times 2/5, right? The 5s are going to cancel. So I get 2y plus 2y. So 4y minus 100 equals 0, right? So 4y minus 100 equals 0. If we solve that, we're going to get y equals 25, right? So I'll put that up here. That's our first value. And then x equals 2/5 y. So if we plug in a 25 there, we're going to get x equals 10. Okay, so that's our optimal value. If we wanted to get our functional value here, we would plug these in. So we would end up with 10, 25, or 10 times 25, which equals 250. That's our functional value here, right? That's the optimal value we get given this constraint. Okay, and so if we wanted to get lambda, again, we can go to one of our equations over here. Lambda is 1/2 x. Okay, so x is going to be 10, so half of 10 is 5. So we get lambda equals 5. All right, so these are all the possible things we can solve for in a Lagrange equation. Generally, we're just looking for the optimal point, that's the x and the y. So occasionally we'll ask for the functional value, what is the optimal value? That's the 250. And sometimes we'll ask what's lambda? And so in this case, lambda equals 5. If you want to try the third one before we go through it, go ahead and hit pause and then come back once you have a solution. Okay. So here, for number 3, again, we're going to start by setting up our Lagrange equation. We set it up by doing our function minus lambda times the constraint. And then we need to find our partial derivatives. Hopefully by this point you're feeling pretty comfortable taking these partial derivatives. The partial derivative with respect to x, we get 2x minus lambda times 8. Partial with respect to y is going to be 6y minus lambda times 6. And the partial with respect to lambda, we know is going to be negative times the parenthesis, 8x plus 6y minus 88. All of these have to equal 0. Okay. So again, we're going to pull our x and our y here and see what we come up with. So if we bring the lambdas over for both, we end up with 2x equals lambda times 8 from the first equation, and 6y equals lambda times 6 for the second equation. So you can see on the right-hand side, they're not the same. So we need to divide by the constant so that they will be the same. So for the first equation, we divide by 8. So we end up with 1/4 x equals lambda. On the second equation, we divide by 6. So we end up with y equals lambda. Since they both equal lambda, they can now equal each other. So we get 1/4 x equals y. Well, that's convenient. It's already solved for y, so we don't need to do anything special to solve further. So once we have our relationship, we want to go back to our constraint. So we have negative 8x plus 6 times y, but instead of y, we're going to have 1/4 x minus 88 equals 0. Excuse me. So when we simplify here, we're going to bring the 88 over to the right, and we want to look at what's left on the left. So now we have a fraction in terms of fourths. So instead of 8x, if we were to turn that into fourths, we'd have 32 fourths plus 6 fourths. So we'd have 38 fourths x equals 88. So now here, if we want to solve, we can multiply both sides by 4 over 38. So x is going to equal 4 times 88 over 38. Okay, so we can simplify this a little bit. So if we divide the top and bottom by 2, right, we have 2 times 88 over 17. right? And 2 times 88 is going to be what? 176. So you get 176 over 17. Okay? So again, we got this just by algebraically simplifying this. So now we have our x value. And our y value is going to be 1/4 of this value. So y will equal 1/4 176 over 17. So let's see. So 4 goes into 176. Let's see, it goes into 17 4 times, and then the remainder is 16. So it's going to be 44 over 17. Okay. So again, if you wanted to get the optimal value, you would take these fractions and plug them back in. I'm not going to do that because I don't have my calculator, but you understand how to do that. And fortunately, we also have that y equals lambda. So lambda is also this 44 over 17. Okay. So let's move on to the next one. Okay. Again, if you want to do it separately, you can hit pause and then come back. Again, we start by setting up our Lagrange equation. Hopefully you're feeling comfortable now with how we set these up. Now we take our partials. Partial with respect to x will be 5y minus lambda times 1. The partial with respect to y will be 5x minus lambda times 3. And the partial with respect to lambda will be negative x plus 3y minus 24. Okay, so we want each of these to equal 0. So we start with the partial with x and y, and we solve both of those. So we get 5y equals lambda, and 5x equals lambda times 3. So for the second equation here, we're going to have to divide both sides by 3 so that both have a lambda on the right. So that becomes 5/3 x equals lambda. So 5/3 x equals lambda and 5y equals lambda. Therefore, 5y equals 5/3 x. Right? If we solve for x, we can multiply both sides by 3/5. When you multiply on the left, the 5's cancel. So we end up with 3y equals x. So there's our relationship that we need. Now we go to our partial with respect to lambda. Okay, instead of x, we have 3y. So 3y plus 3y minus 24 equals 0. So we end up with minus 6y minus 24 equals 0. We can neglect the negative here because if you multiply both sides by -1, that'll take care of it, or we know that whatever's in the parenthesis has to equal 0. So 6y minus 24 equals 0 tells us that y is going to equal 4. Okay. And then over here, if y equals 4, that tells me that x equals 12. Okay. So again, if we wanted to get our functional value, we would take the 4 and the 12 and we'd come up and plug it back in here. So we would do 5 times 4 times 12. So 5 times 4 is 20. 20 times 12 is 240. So our optimal value here for 12, 4 is 5 times 12 times 4, which equals 240. And then if we wanted to get our lambda, looking at our lambda equations back up here, lambda is y times 5. So if lambda is y times 5, that tells me that lambda is going to equal 20. Okay, so when you do these and you find these optimal points, it is a lot of algebra, but it's really about the structure and the process. There's one more here. I'm not going to do this one. I want you to try this one on your own, and I want you to do it. And then if you have questions about it, I want you to bring it on Thursday, and we'll talk about it then. Okay? So good luck. I hope to see you guys soon, and keep practicing, keep studying, and I will see you guys on Thursday.